now we'll continue. Okay, so what we did, we considered covariant derivative for orbital reference system. By the way, you should need to see it, it should be minus. Okay, here please correct, because we have had here minus. Finally we have a plus, so it should be minus here. So let's continue, and we obtain two expressions for the covariant derivative for covariant and for contravariant vector. And now we will consider how it is work for the in the first. We obtain also such a called gamma KIL, such a call which called Christoffel symbols. They also called as a affine connection. We can use Christoffel symbols. And again, we understand that the differences between covariant derivative and normal, I will say, derivative, due to the fact that we have additionally the summand, which tell us and which consist of some property of coordinate system. So we will see today is that the Christoffel symbols depend on metric tensor. So, and it's proof exactly that it's related with the property of coordinate system. What is important that also we understand that, and we can prove that Christoffel symbols is not tensor. And it's even can be understandable, because if we are in a flat space, or in, as we say in Galileum, and from the point of general relativity, we can tell that we are in a local inertial reference system. So flat space, local inertial reference system. Sometimes I can use this one, local inertial reference system. It means that, for example, if we have a curved space, we can choose some local space which we can consider as a flat space. Or, for example, since we would like to build a general theory, we understand that we can freely go from general coordinate system, which can coincide to the curved space, to the flat space, which is related with, from the point of general relativity, which is related with inertial reference system. Curve is not inertial reference system, as we understand. So, in principle, we can understand why Christoffel symbols is not tensor, because in inertial reference system and flat space, all component of Christoffel symbols equals 0. So, and it's understandable that if it could be tensor, it means that if all components of the tensors are equal 0 in one reference system, it will be equal 0 also in another reference system. So, but for this symbol, it's not like this. Okay, so this is just a proof that Christoffel symbols is not a tensor. But when we work with the Christoffel symbols, we can use the general rule of raising and lowering of indexes. So rules of raising, lowering of indexes in gamma. Okay. So what it means? It means that if, for example, we have Christoffel symbol gamma, let's put it M, K, L, and we will apply metric tensor IM, so it will work the same as with the tensor. We will have finally the index M will go down, and we will have gamma I, and let's put some space just to remember that I come to us from top, KL. Sometimes you can put punto or point. So otherwise, if we have, for example, gamma M KL like this, so if we apply metric tensor like this, so M is a summation index, we will obtain gamma I KL. So this is in principle rules which we would like to know. Now let's consider the equivalent derivative from the tensor of the second rank. Let's go. Okay, come back. Some problem with the connection. Can you hear me?
Yeah, we can.
But without screen, yes?
Yep.
Okay.
Yes.
Okay, so I can write variant derivative for tensor of second rank. It was important for us because we will work with finally with such a kind of tensors. Okay. So what I will need to obtain this expression, I will need something which we received before. Ta-da-da-dum, ta-da-da-dum. Yeah, this one. So this is this expression for a change of the vector when we move it along the coordinate axis. Okay, this one. So so let's put it here. Delta AI equal minus gamma I KL AK DXL. And now I want to, so what we obtained before, and maybe I even will repeat it because just to put it together. So for a differential, okay, for the differential, just okay, it's not a covariant derivative of a tensor of the second rank for the first rank. I will put it here just to look at this. So differential, just remind, differential we determine like as this point comma L DXL for contravariant and for covariant. Like this. So, and I will remind that this covariant derivation is just a normal derivative plus symbol Christoffel, which take the index I, the top. After this, should put in the bottom index L and summation index. Okay, and for covariant mnemonic, it's very simple to remember. So this is normal derivative plus gamma. Sorry, there is here the different in the sign minus gamma. And here we need to put, since here index below, so we put it here also below, also the second index below, and here summation index. So this you can put in frame to remember that this is expression for the covariant derivative of a tensor of first rank, which is the same that vector, okay, vector. And now we want to see what it will be if we have a tensor of the second rank. So it means that we have two indexes. We can generalize the expression which we obtained if we will use the Leibniz rule and can represent in simple way, just to do it more quickly, we can represent the tensor of the second rank as a multiplication of two tensors of the first rank, AK multiply on, sorry, it's better to AI BK, okay? So in principle, we can prove very simply, we also obtain a tensor. So the transformation will be also tensor. because it will be derivative x by x prime like this. And now we will apply the operation of delta. So the delta, which we apply to t I k equal to delta ai bk. So due to rule of Leibniz, we have the following. AI delta bk plus bk delta ai. And we will remind that these differences when we make when we move our vector on the coordinate axis like this. So we will put it in our expression what it means. So we will have minus ai, this is the same, and instead of delta bk we will write expression through the Christoffel symbol. So, but we need to take into account the corresponding indexes. It will be gamma k, because gamma takes this index k. Below we will put, for example, lm bl dx, sorry, yes, bl dxm. And for the second summand, so we again will have minus bk gamma. As an example, of course, we see we consider here the contour variant tensor. Of course, we can do the same for covariant tensor, so we just need to put b with the lower index. So bk gamma take index I, lm al dxm. So, and we can take out dxm. So, and we have I bl gamma k lm plus and bk gamma I lm. If we now come back to our definition of multiplication of A on B as a new tensor T, and also I want just, it will be convenient and not important to do it, but it will be convenient just to use, to change indexes. So, because it will be convenient for the following. So I can do it because I will change only summation index, and now you also, it's a training to see on this procedure. So since M and L, this is summation index, I can freely to change them, but everywhere, okay, it will be the same. So in this case, I write dxl. Now, instead of A multiplied on B, I will write T. I m gamma k ml plus T mk gamma I ml. So it looks that I didn't do any mistake. And we start from this place and we come to this place. So here I will put, so this is equal delta T I K. We can check, such a rule of conservation of indexes all time when you obtain something, to be sure that you didn't didn't do any mistake. So you can estimate the indexes. Here we have on the right side IK, and here MM. So IK we have L. So only two indexes, MM and L with this L. So everything looks for the first view okay. Now I will remind us that, again, look here, that the general determination of differential dt ik, this is what? This is normal derivation, the normal differential, the tik minus delta tik. So the same what we did for vector and covectors. Or if you want to write it through the covariant, in principle we can continue like this. So what is this? This is so write what is a normal differential. This is tik normal derivation L on dxl. This is just through mathematical analysis, just to explain that this is dtik dxl. So we just choose this this writing through using the comma, and minus with all these beautiful things which we have. So it is, since it's minus, it will be plus, and tim gamma k ml plus tmk gamma iml dxl. And if I want to write, so this is what we obtain. This is differential, the tik. In principle, we can already put it in some frame. If you want to write derivative, we need to do what? We need to divide formally the xl here, the xl here, the xl here. Due to the definition of derivative. Okay, so I will come back. So it means that finally I can write, maybe I will not have here place. So next page. So it will be t I k L. So as soon as I put point comma, it's understandable that this is covariant derivative equal. To remind that this is d t I k. So the corresponding covariant differential to dx. I will write it only once. And this is equal to the normal derivative and plus. Okay, plus. Tim gamma kml plus tmk gamma iml. So this is final expression for the tensor of the second rank for the contravariant. This is you can write it. This is the expression for covariant derivative of the tensor of the contravariant tensor of the second rank. So if we will do the same and it's understandable, we can make the same procedure. We will obtain, I will write it because it will be useful for us for the following. The covariant derivative for the covariant tensor of the second rank. Okay, so tik covariant derivative L equal, again, understandable that we will have a summand which represent normal derivative. And we also will have a structure, but with minus, like t multiplying gamma minus t multiplying gamma. And now we will need to put the corresponding indexes.
Maybe normal derivative, we need to put indexes
of course. Thank
in
you very
lower
much.
part.
Yes, of course. Thank you. Yes, of course. Okay. So now we need to put here the indexes. In the first, it's the procedure such a time that all time gamma take one of the index which correspond to the derivative and the one of the index which correspond to tensor. So, for example, it will be IL. You can see that gamma took index I, the first index, and L. After this, it's understandable that one of the index will be summation index. So we need to put here also summation index. And after this, we put the last index, which we have, K. The same here. So now we will take the second index, K, KL. Again, we understand that here should be the summation index. Here should be summation index and I. So you can feel the logic of or mnemonic rule how we can distribute indexes. And by analogy, it's even not important again to prove it. So we understand that we also have a mix.
I think that in second part, in third term, we need to put TIM. No, because we have kind of the same T terms.
Okay, yeah. Okay. Here, I mean, am I? Or I am.
No, I am.
I am, yes, okay. Ciao, ciao. I would like, but I have my lecture now. I will join for lunch. Sorry, okay, can you repeat what we need to put here? I am, yes? Or am I?
Yes.
I
I
am.
am.
Okay. So, and the third one, so the tensor, the mixed tensor. So the mixed tensor of the second rank, I, covariant derivative L. Again, we understand that we put it like this. And since we have one index with contravariant, one index covariant, so we understand we need to mix it to use the formula, the idea above. So we can write minus gamma take in this case KL M A T I M. Okay, this we used for the contravariant component. Yeah, looks right. Plus gamma. Sorry for covariant component. Plus gamma I M L A M T M K. So let's check the indexes. I K L I L K L. So it looks like right.
Can I ask another question?
Yes.
How can we define which we need to write minus or plus? Yeah.
This is due to this is not so for contravariant all time you have a plus, for covariant you have a minus. This is I gave you the home task, which is I even want to say that I would like to refuse this home task because it's not simply to show why for one derivative we have plus, for example, here, for a contravariant, and for covariant minus. It's related with this mathematics when you write all these derivations by coordinates. So if you want to understand it, I can later to send you this proof, but even somebody already sent me the task which I gave, but I forget that it's really there is some not so clear. So it's not so simply to show why in this case we have a plus and for the covariant component we have a minus. But you just can trust me that, and look here, you can see. So this is for contravariant vector, and this is for covariant vector. Here you can see minus. But this is due to this play with the derivation of coordinates. It just appear as a minus if to do everything careful. So how you can understand here, where is the plus, the same as with vector. For contravariant vector, where we have these indexes above, we all time need to put plus. If you have the covariant tensor, we need to put minus. If there is a mix, so here, for this index I, which is above, we need to use this summand, which is with a plus. And for this index, which below, we use this summand, which is with a minus. So this is main idea. Why here, for the mixed tensor, we have a minus and plus, because one component is covariant and another contravariant index. So I hope I give an answer on your question.
Yes, thank you.
I understand that maybe not everything can be incredibly clear, so I try to give you the proof, but of course, due to the fact that we don't have a lot of lectures, and we would like to succeed finally and to reach general relativity and cosmology, so I need to consider it with not incredible detail. But in any case, you can see that I try to give you the proof which allow you after this to work independently. So this we can put in frame, and this is what we will need, which is covariant derivative of a tensor of second rank. So for all possibility, contravariant, covariant, and mixed. So now we will consider some rules of covariant derivative. Okay. And I just want to say why, I give you, so it's really, so for now, it looks like mathematics, but finally, to understand, and my opinion, to understand the equation, of course, you can write in Wikipedia about Einstein equation and in general, which is solution like this. But to understand deeply what is it, you of course need to consider it much more deeply. This is the point. Otherwise, it's enough to look discovery. So the first, and especially to see some miracle when you discover that some complicated equation can give you really some, with much more simple ways, information about evolution of universe, or what is the dark energy, how this involve inside the equation, how this is support the observation like this. Unfortunately, I must say that that you have we're not against the educational process, but from my point of view, you have a lot of lectures during this year. But from my opinion, it's better to add something much more physical, lectures, and even to add something for cosmology. But so this is what we have. Okay, the first one, come back to science. So if we have a scalar function phi, so distribution of scalar, so it means that we have a value of some scalar value in any point. Okay, in this case, the covariant differential equal normal differential. because we don't have this this change due to curve axis. So, and of course, it means that the covariant derivation, we have just a simple derivative. Second one, so we also can apply Leibniz rule if we have this multiplication AI as an example, BK covariant derivative L. So we have AI covariant L BK plus AI covariant L. The third one, so we need to understand that, and it was our goal in the beginning, our goal was to find the differential operation such a way that this operation can take a tensor and create, due to this operation, again tensor. So it means that covariant derivation, I will put like this is tensor. Applying to the tensor, create also tensor. And in principle, you can see that the final tensor which we obtain, so if we here apply the covariant derivative on the tensor of a second rank, finally we obtain the tensor of the third rank. But also we understand that since finally we have a tensor, we can apply the same, by definition, we can apply the same rule of raising and lowering of indexes. So it means that if we have a, for example, I, L, on an example of the rank, the first rank tensor, if I will apply symmetric tensor GKL, finally I will obtain A, I, and you can see now that what I am doing. So there's a summation index L here and L here, but I take it in, together with this point, comma. Okay, so I can write like this. And otherwise, if I will have A, I, sorry, I, of course, L disappeared here. It's a mistake. I need to put here another index next to covariant derivative. Which index I need to put? Tell me, please. K, of course, K. So, and if I have A, I, I'll put like this. I can write even like this. So, and I can come back to for the covariant derivative, which will be below. So what I need to do, I need to put G, K, L, A, I, L. So this is some general rule. Of course, it can be applied for a tensor of other rank. For Um, okay, I would like again to repeat.
So
Yes.
a 5-metric tensor only only changes only derivative, but does not any effect on tensor.
Because look, I put here the index, summation index, which I put here. This is syntax which
Okay.
correspond to derivative. So
Okay,
of
okay,
course, if I
understood.
will, yes, I can. A little bit
Okay,
later, we will see. Yeah,
if
we
here
will
will
see.
be ki, it will affect tensor, but not affect derivative.
Yes, but we also need to be careful because exactly a little bit later we will consider it because can we, for example, to put metric tensor under operation of derivative or not? So, and we will see what we can do with this. So, but for this case, yes, we can do like this. 4, I would like also again to repeat that and to put it here as a property that Christopher symbol and this right is not tensor. I already said about this, but it's not tensor. And to again to put here to remark that the Christopher symbol behave like tensor only for linear transformation. Only for linear transformation, because why? Because we have the second derivative, as you remember, for the stop symbols, and just you make a 0. The 5th property. So in general, if we will consider such kind of construction, so what I made, oops, sorry, I change the lower indexes, KL and LK, change order. And this combination will be create tensor. Without proof to check, but if you would like, you can check it. But if you will consider such a kind of combination, it's create tensor. This tensor, which has corresponding indexes, called torsion tensor. Torsion tensor. Torsion tensor of space. But I want to say. So, and I must say that in general relativity, which grounded on the equivalent principle, it's postulated and considered, let's try to say that general relativity as IKL equals 0. So this torsion tensor equals 0. Why we can consider like this? Again, because and we can feel it why torsion tensor should be 0. We can feel it just due to simple logic, because all time we understand that we can choose the local inertial reference system, so which correspond to the local flat space, for which we have all Christopher symbols equal 0. But it means that in this case, in this reference system, which we choose as a local inertial reference system, torsion tensor also will be 0. But if, as by the definition of tensor, if tensor equals 0 in one reference system, one coordinate system, it will be equal 0 to any other reference system. So you can write, but since this is tensor and it's equal in one reference system, it means that this tensor should be equal also in 0 in any reference system. And it's a proof that Tarsian tensor equals 0. So again, why I say that it's ground on the equivalence principle of general relativity, because the idea of general relativity is a joint all reference system. Again, you remember that special relativity working only with a special reference system. This is inertial, but general relativity is all reference systems. So it means that we need to build theory for any reference system, including inertial. What it means? It means very good things for us for the following, because it brings us very important property of Christoffel symbol, because they are symmetrical with respect to the change of the order of lower indexes. So you can write that Christoffel symbols are symmetrical with respect to change the order of the lower indexes, which is really immediately make much more simple many things with which we need to work, because it means that number of non-trivial components really reduced. So when we have an end, we have plus 20 minutes, yes? Right?
Yeah.
Okay. So now we will consider important relations. No, in the first we need to consider the connection of Christoffel symbols with metric tensor, which is very important because you could see that expression for Christoffel symbols is, I must say, disgusting in the sense that it's some double derivative from the coordinates and multiply again in derivative. When you look in this, you say, "Ah, mama, how I can work with this? It's I can make a mistake very simply." So, but now we finally will obtain a beautiful expression of Christoffel symbols through the metric tensor, which you will train with home task how to work with this. But in the first, to do this, we need to prove, and this is one of the property of metric tensor, that covariant derivation of metric tensor equal 0. So to do this, we can consider covariant vector, and let's apply the operation of differential. So DAI. So since, as we know, the covariant derivative and corresponding differential create finally also tensor, so we can apply the rule of raising and lowering of indexes. So I can write that it will be GAK, K, D, A, K. From another side, we can, the same tensor, same vector, so we can also consider as to apply this rule. This is like this. And after this, we can apply the operation of differential, put differential. Okay, so DAI, it means applying on JIK, is equal plus K, J, I, K. And now we can compare this one with this one. So from the left side, you have the same. So we can join this, and we have IK, ZIK equal this disappeared, and we have from this set D I equals 0. Or if we divide formally on dx L, so we can write that GIK covariant derivative L equals 0. Let's put it in frame. And we can see a very important property of metric tensor, that metric tensor behave like a constant during this covariant derivation. So if we will apply the operation of to find the derivative from the metric tensor, so it will be 0. And it's very important because it means that we can put, if, for example, we will see now, if we will have some expression, so it was exactly a question about this, so we can put inside of the operation of derivative, we can put inside the metric tensor. Now let's find the expression for Christoffel symbol through the metric tensor. We can use this exactly this rule as this result. And okay, now look, I will remind you what is covariant derivative from the tensor of the second rank. So we just wrote before, so we can write it. It will be useful for us in space, so I will put it here. A. So if I have some tensor of the second rank covariant, I apply covariant derivative. It will be normal derivative and construction such a way. So I remember that this is covariant tensor. I need to put 2 times. So if this covariant derivative of the tensor of the second rank, I will repeat twice this construction gamma A minus gamma A. By the way, we can generalize, I didn't put it, for the tensor of the arbitrary rank. And it's understandable that as much as you have the rank of the tensor, you need to repeat this part, okay? So, I just not to do a lot of things additionally because we are physicists, we are not mathematicians, but we can generalize it freely. After this, I need to write. So the first gamma take I and take the index of derivative L. Okay, so the index of summation M K. Okay. Gamma take the second index K L index of summation IM. So, and now I want to apply this to metric tensor. Okay, so instead of A, I will put G. So what I write? G, IK, covariant derivative L, which is now we know that it's equal 0. But if we will rewrite, if we will write a full expression for the covariant derivative, we have GIK normal derivative minus gamma EL ILM GMK MK minus gamma KLM GIM. Okay. So, and from this, I obtain expression for G I G I K L equal gamma M I L G M K plus gamma M K. Just rewrite everything. E M. So now I will do the cyclic permutation. Okay, the cyclic permutation. The cyclic permutation of the lower indexes. So what it means? So I put L here and cyclically. So I will obtain the expression G L I K. To be not here, it's better because it should be careful. So I will do it here in the first expression. Okay, so I can consider this what it gives me the tensor which has such kind of indexes. In this case, I have normal derivation. Again, I have a construction minus gamma G minus gamma G. And now I need to put indexes. So it's not a point that the same way I can make a cyclic permutation on the right side. I just need to look on the distribution of indexes here, and after this to put here indexes corresponding to covariant derivation. So, and I again remember that the gamma take one of the index here, and then index K, which is with covariant. After this summation index, and which what we have. Here, I remember gamma take the second index I from G and covariant index K. Again, I need to put here M, ML. And from this I obtain, I can put here in frame because it will be useful for us. So from this I obtain that G, L, I, K
Sorry,
equal.
possibly in third term we need to put gamma m ki and glm.
But we already know that it's a symmetrical
Or
relative.
it's
This is the
doesn't
gamma
matter.
symmetrical, yes. So, principle, of course, the metric tensor can be asymmetrical, but in principle, you will see that for many cases it's asymmetrical. So, but thank you that you check for this. For here, for this case, we cannot to check with this. Of course, if you have a derivation, this is much more important. Okay, so we can write gamma LK M GMI plus gamma M IK GML. So this is the second expression which you will need. And we again can make a cyclic permutation here. Okay, put K in front. So it means that G K L I equal 0 equal G K L normal I minus again gamma G minus gamma G. And again, this will be Ki M M L and here L I M M K. So, and finally I have G. I wanted that everything will be in one page, but okay. K L I equal gamma K I M G M L plus gamma M L I G M K. So, and this is the third one which we need. And after this, I could even make it much more simple because, as you remember, I don't like to do it here, but so you can rewrite it because I also can apply the operation. For example, look here. So what it means? So I will put here 1, here 2, here 3. Okay, 1 I can rewrite like this. GIKL equal. Now I look here. So applying GER on simple Christoffel, I can write. It will be gamma L gamma KIL KL plus gamma IKL. Agree? So this is just since I apply here the metric tensor, I just make the index M lower index. With the second one, I can write like this. So G L I K equal gamma, and look on this one. So it will be I gamma I L K plus gamma L I K. So this is from 1 This is from 2. And the third one, the cyclic K, I, L, I equal. So, and I look on this is applying of here again. Applying of from here, applying of from. So it will be L gamma L K I plus gamma K L I. So and this is from third one. What now I can do? I make this plus this and minus this. So it will mean that this is GIKL plus GLIK minus GKLI. And after this, I can see that if I do this, so I can look that due to symmetry of the relative to the indexes, so this will disappear and this will disappear. Okay, this will disappear. IKL, LK, this will disappear. So, and I will have, and this one the same. This one equal, this one. So this does not disappear, sorry. I already rush. So this is the same because this is with plus. So it will be with plus. But this one will disappear. Okay. So and finally we will have 2 gamma I K L. Or again to come back the index, so I can write here 2 gamma I K punta K L punta. I put here just to remember that I come from us after the applying of this rule of lowering index equal G I K L plus G L I K minus G K L I. If I will apply here, equal, so I will multiply the left and right side on GAN. I can rule to do it. So I want to make index I in the top. So it means here I also need to do like this. Finally, I will have from the left side gamma N KL equal 1.5 GIN, and here sorry, K minus GKLI. So finally I obtain, it's already 20, okay. I obtain the expression for Christoffel symbols through metric tensor, which is very important to use in the future to work with a metric. And if you can see later in the next lecture, I will show you the mnemonic rule, and we very quickly to work with some simple metric as an example, and you will have your home task to work with some little more complicated metric. Okay, it's all for. I will need to make screen. So do you have some questions while during this time when I make screenshot the presence? No any question? Okay, so see you on Friday and good week.